find the inverse of the function f of x is equal to the square root of x plus 2. So anytime you're asked to find the inverse of a square root, it's going to be crucial to start by finding the domain and range and sketching a graph. We'll then be able to use the domain and range and the graph of the original function to define any restrictions on our inverse function. So let's first start with our domain here. So we know we're working with an even root radical, which does not exist if the inside's negative. So we're going to go ahead and set our inside here, x plus 2 greater than or equal to 0, to prevent negative numbers. So we're going to solve for x by subtracting 2 from both sides of the expression. So 2 minus 2 leaves us with 0. And we can see that x must be greater than or equal to negative 2. So we can say, therefore, the domain of the given function is all real numbers greater than or equal to negative 2. So now to find the range of the function, the range of the square root, we start with the fact that we know the radicand, or the inside, must be greater than or equal to 0, and we want to build up to the given function here, f of x. So to do that, we'll first take the square root of both sides of the expression, which leaves us with the square root of x plus 2 must be greater than or equal to, the square root of 0 is just 0. And again, if we look at this function that we're given, we can see the square root of x plus 2 is equal to f of x, which by definition is y. So therefore, the range of the given function here is all real numbers greater than or equal to 0. So we're now ready to go ahead and sketch a quick graph of our given function. So this is our y-axis and our x-axis. We know that the square root is being shifted 2 units to the left. Right, and we see that the smallest x value, or the first x value, is negative 2. The first y value is 0. So our ordered pair here, our x-intercept is negative 2, 0. So this is our given function, f of x is equal to the square root of x plus 2. So we can even make a little note to ourselves that this graph, the shape of the graph, is half of a parabola. So we'll want to keep this in mind because we know the inverse function should be a perfect reflection, or the graph of our inverse function should be a perfect reflection of f of x across the diagonal line, y is 0. Right, so by the time we're done, we'll have a perfect mirror image of the graph across this line. So we're now ready to go ahead and find the inverse. So again, our given function here is f of x is equal to the square root of x plus 2. And the first thing that we want to do is replace f of x with y. So we have y is equal to the square root of x plus 2. Step 2 is to interchange the variables. So we are going to switch the x and y coordinates. So we now have x is equal to the square root of y plus 2. And we are now ready to solve for y. So I'm just going to rewrite my expression here. The square root of y plus 2 is equal to x. So to solve for y, or to get to y here, we remove the square root by squaring both sides of the expression. So the square and the square root undo the effects of each other, leaving us with y plus 2 is equal to x squared. And to isolate y, we subtract 2 from both sides. So 2 minus 2 is 0. leaving us with y is equal to x squared minus 2. And then last but not least, we replace y with f inverse. So we have f inverse of x is equal to x squared minus 2. So this is not our final answer, though. We want to be careful. If we think about the graph of this function, this inverse function we just found, we know that it is a parabola shifted down 2 units. So we shift down from the origin 1, 2, and our parabola has a vertex at the ordered pair 0, negative 2, and the same shape parabola as our squaring function. So this is f of x is equal to x squared minus 2. And looking at this graph, we're reminded that a quadratic is a polynomial. So the domain of this inverse, we'll label this on the graph as well, but the domain of our inverse is all real numbers. It's undefined nowhere. And then looking at the graph, we can see that the smallest y value here is negative 2. So it has a range of y greater than or equal to negative 2. So it's important at this point to recall one of our properties of inverse functions, and that is that the domain of a given function must be equal to the range of the inverse, and that the range of the original function must be equal to the domain of the inverse function. So let's check this to make sure it's holding true. So we found, at the beginning, we found the domain of the square root of x plus 2 to be all real numbers greater than or equal to negative 2, which we can see is equal to the range of our inverse function. So the first part holds true. And then when we think about the range of the original function, recall that that was all real numbers greater than or equal to 0, which does not equal the domain of our inverse. So we want to fix this by adding a domain restriction to our inverse function. So we want to restrict it by making sure that x is greater than or equal to 0. So therefore, the final answer for our inverse function here is x squared minus 2, such that x is greater than or equal to 0. So now, if we think about the graph of the original function and our inverse function together, we'll see that they are symmetric across that diagonal line. And we know we had shifted the original function 2 units over, giving us that x-intercept at negative 2, 0. So this is f of x is equal to the square root of x plus 2. And then with the domain restriction on our inverse function, it's been shifted down 2 units. So it has that vertex still at 0, negative 2, but we're only now considering the right-hand side of the graph. So this is f inverse of x is equal to x squared minus 2, where x is greater than or equal to 0. And we can also see now, if we think about that diagonal line at y is equal to x, we can see that the function and its inverse are perfectly symmetric across this line.